I will begin. Is it bouncing?
Yeah.
Yeah, okay, cool. Dear Father, we thank you for this day. Thank you again for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I've begun to explain to you guys this magical world of the Laplace transform. And so today we're going to talk about Laplace transforms with the application of discontinuous. I can't spell US. Discontinuous cases. All right. In other words, this is the thing that we really have no choice. Well, I mean, I guess you have other choices, but this is the best choice, I think, that we have to confront problems with discontinuities. And certainly in engineering, you come to things that have discontinuities, right? Like, for example, if you think about, oh, this room still has, behind you, Josh. Is it? If you could hit there's things behind you, hit both of them, put them down. Yeah, right. There we go. And then put it back up again. Thank you. As you can see, the light turning on off and on is a discontinuous thing, right? It's not like, it's like, oh, the lights are on, and then they're like a little bit off, and then they're all the way off, right? No, it goes from on to off, right? That's on to off. That's a discontinuity. And that's the kind of thing we can handle with discontinuous cases. Now, it's good that we're giving this lecture. I mean, I'm giving this lecture. I hope you're not giving it in the second story, because this is, it's sort of time travel in this building. As you go to the topper floors, the upper floors, it's kind of future travel, right? So in the lower levels, we still have these things called light switches. But see, it would be more difficult for me to illustrate this in like a third or fourth story classroom, because there we've got all these automatic lights, and and sometimes you don't even have control over the hose. I learned the other day. Okay, I'm digressing, obviously. All right, so let's get to it. The basic tool is the unit step function. The unit step function gives us a way to give formulas. And so here it is. U of t minus a is going to be 0 if t is less than a, and it's going to be 1 if t is greater than a, right? I suppose you could define the sort of more basic unit step function. U of t is, well, it's 1, good grief. It's 0 if t is less than 0, and it's 1 if t is greater than 0. I don't know. Which one of these do you want the equality to go on to? Not really. 1? Okay, great. There we go. I will forget that. I'm not sure if it really matters. It doesn't matter to us at the moment. Okay, so let's look at a graph of this for just a second. So what we're looking at, the graph is kind of boring, right? It's 0 until you get to a, and then it jumps up to 1, right? And there you go. So this is this time, of course. And we're looking at the graph of u of t minus a. Now, what if I had b larger than a, right? And I looked at a graph of u of t minus b. And let's assume that a is less than b, all right? In other words, the b is like here maybe, right? Then this one has a graph that looks like this. Right? What happens if we subtract the unit step function from based at b from the unit step function based at a? What happens if we look at the difference of these two? put these two things together, if you look at, let's say, the gate function from a to b, which we'll define to be u of t minus b minus u of t minus a, then if you think about the graph of that, you got three cases, right? So the first case, it's like this and this, right? So it's 0 all the way over to a. Oh, I messed it up. Which one should I subtract from which? I need to, sorry guys, I should do u of t minus a minus u of t minus b is what I want. Because I want this thing to jump up to 1 at a. Okay? Then I'll think about the middle case in brown. What we got? So going between a and b, right? And here, we have 1 minus 0, right? So we just have 1. And here we're at b. And then in the third case, of course, what happens? We're back to 0 again, right? So there you go. We could write out what we have here. The gate function from a to b of t has three cases, right? It's 0. We could say 0 if t is less than a. And we could say it's 1 if a is less than t is less than b. And we could say it's 0 again if t is greater than b, right? And I guess to be, again, I don't really care about this does not matter too much to me, what it actually is at the gluing points, but technically speaking, I suppose the equality is here and there, as I've constructed it. So this is a gate function. Now, we could also define, and we should define, let's say, g of a comma infinity to just be what? That would just be u of t minus a. See, because what that is it's 1 at time a, and it just continues to be 1 after that. So it's kind of an open gate in some sense. Okay, so yes?
This is somewhat related, but if I take the function, that function, from b to infinity, I could say that that's continuous, right? Just from values of b to infinity.
Oh, okay, yeah. If we just focused on from b to infinity, it would be continuous, right? If we stay away from the places where the different cases glue together, each piece of it is continuous. So these are piecewise continuous functions. Yeah, this is true.
Well, on that note, then if I take the function from negative infinity to a,
Mm-hmm.
would that still be continuous? Because there's a jump discontinuity between point A and everything less than A.
I suppose it would depend on whether or not you go from one side of A to the other. If you transition from one side of A to the other in your domain that you're thinking about, then we have a discontinuity. If A is on the edge of the domain, it could still be continuous, yeah.
Really? Okay.
Mm-hmm. Well, continuity is a question which requires context, right? So like a function could be continuous with respect to one context, one domain, and not continuous with respect to another. For example, f of x equals to 1 over x. What have you started? F of x equals to 1 over x is continuous on its domain. What is the domain of f? Well, the domain of f is, we'll take a real perspective. It's the reals with 0 removed, right? So minus infinity to 0, union 0 to infinity. Now, you've probably been taught in pre-calculus that that's discontinuous, right? But that's an abuse of language. See, because the definition of continuity was a function is continuous if the limit as x approaches a of f of x is equal to f of a. That's the definition of continuity. And we adapt that to left or right limits as appropriate to the edges of, right? But this domain has no edges. So the discontinuity of this function is actually outside its domain. This is not a discontinuous function. In fact, it's continuous on its domain. So, but we would tell students in pre-calculus this is a discontinuous function because in pre-calculus we take the perspective that the sort of primordial, if you will, oh, I keep saying that. I can't say that here. The backdrop, the blank canvas on which you draw things for a function starts with the whole real line, and then you delete points from that. And if points are deleted from that blank canvas, that's a discontinuity, which is at odds with the careful technical definition of continuity that we share with you guys in Calculus 1, namely that a function is continuous if the value of the function at the limit point is equal to the limit of the function at the point. So, yeah, what did you start in here? Hey. But people disagree about this, how this should be taught and discussed. I asked a question about this on the Math Educator Stack Exchange a couple of years ago, and people's viewpoints vary. And, but anyway, educators' viewpoints vary. All right, so let's put this into practice. So if I have, say, f of t defined by, let's say, 1 for 0 less than t less than 7, and then sine t for between 7 less than t less than, I don't know, 3 pi, and then e to the t for t greater than 3 pi, right? And let's agree to not care about which case it falls into at the gluing points, because that's not something I want you to worry about. Right? So if you'll allow me to be sloppy, I'm not going to even say what happens at 7 and 3 pi. Okay? Because, yeah.
So, if you do a question like this on the test, and you don't put in like what happens at the gluing points.
You do not lose points. Right. Unless the question is about Fourier transforms, where we have something interesting to say there. But that's later, so don't worry. There, it turns out that when you calculate the Fourier series to represent a function, if there's points of discontinuity, the Fourier series it conspires to give you the halfway point between the jumps. But here, nothing so interesting happens. So I mean, really, well, we're going to take the Laplace. The thing is, we're about to take the Laplace transform of these things. So Laplace transforms based on an integration, right? What happens if you calculate the area of a function? Let me explain to you why it doesn't matter. So if I have this function, right? And then I take that function and I go, you know what? That's not right. This is not really there. Actually, at that point, right there, the function has this value. You know? And then I ask, what's the area between, between a and b for that function? Well, the area between a and b under that function, the signed area, it's the same for the discontinuous one with this one jump and for the continuous one. Like, the integration is insensitive to a finite or even a countably infinite set of discontinuities. It's called a set of measure 0 if you study things more. So when we take the Laplace transform, we can't even tell the difference between the differently glued together functions, so there's no point in worrying about it. I've now said entirely too much about this issue. So, hey. I was about to say, don't be an Ian. But that seems mean. I saw one say that. Let's see here. I was very disappointed. I was told about protests out in the front steps yesterday, and then I went out. I wanted to see these protests. I was excited. I'm like, protesters on my front steps, and then there's nobody there. Just a bunch of crates. I'm like, hey. And I Googled it. There apparently were people there. I mean, they got a 3-hour permit. But did any of you see the protest in the front? Well, they did some very bad marketing of this protest. You saw it?
What were they protesting?
Was it exciting?
It wasn't that exciting.
They're just standing with signs? There was no chanting or rhythmic clapping or?
There was cookies beside
Were the cookies part of the protest?
I don't know.
Oh.
What were they protesting? Cookies?
I don't know, but there should be more protests. I don't know. I miss protests. When I was undergraduate, there were always people protesting somewhere on campus. It was fun. Usually about something stupid, but anyway. All right. So now that I have digressed considerably, question, can you rewrite this function with an explicit formula in terms of gate functions? The answer is yes. Here's how you do it. So we say, well, what this is 1 times the gate function from 0 to 7 of t plus sine of t times the gate function from 7 to 3 pi of t, and then plus e to the t times the gate function from 3 pi to infinity. Or of course, that's just the unit step function, but now, do you see why that's logical? The idea is the gate function turns on the case just for the case, and then it sets it 0 otherwise, right? So it's like, if you look at it in case 1, it's this plus 0 times that plus 0 times that. In case 2, it's 0 times 1 plus sine of t times 1 plus 0 times this. And then in case 3, these two are turned off to be 0, and that one's left on to be 1 out to time infinity. I don't know. This is a really neat trick, I think. So this one, we have 1 times u of t minus, u of t. How does it go? If I could remember anything. U of t minus u of t minus 7 plus the sine of t times u of t minus 7 minus u of t minus 3 pi plus e to the t times u of t minus 3 pi. Now, if you take this course from an engineering professor who has less patience than I do, they would probably just write down the next step, because pragmatically speaking, this is what you do. So, I mean, it always leads to this. So I've got my u of t, and then plus sine of t minus 1 times u of t minus 7, and then plus e to the t minus the sine of t times u of t minus 3 pi. The step above is not wrong, right? But what I'm about to box, this, we will soon learn how to take the Laplace transform of that. So exciting. My brother sent a response to an email that was funny on several different levels. So I was happy. All right. I can't explain here. Not that it's politically incorrect. It's just too far into linear algebra to you appreciate the joke. You know. Yeah. Really? All right. No. I'm about to be Ian'd again. Let's see here. By Ian, no less. So my point is that this boxed equation is pretty. It's not bad to take the Laplace transform of this. We will soon have a theorem. In fact, it's already on your sheet that says. Let's see here. What's the theorem we want? Formula 8, actually. Let's just use that without deriving it for a second. So the Laplace transform, I mean, I will soon work out why this is true, okay? But for the moment, let's just use it. We have the Laplace transform of u of t plus the Laplace transform sine of t minus 1 u of t minus 7 plus the Laplace transform of e to the t minus the sine of t times u of t minus 3 pi. So we're going to use formula 8. We need to use formula 8, which is sitting on its lonesome you know, right below table 7.2. What is that theorem? What's that result say? It says the Laplace transform. What's the formula say? It says the Laplace transform of g of t times u of t minus a is equal to e to the minus as times the Laplace transform of g of t plus a. So unit step functions apparently generate exponentials in the frequency domain. All right, let's do that. So what's the, well, this one's easy. This one actually just works out to 1 over s as it happens. I'll explain that more later. Let's focus our attention on the next piece. So this will be e to the minus 7s times the Laplace transform of the sine of t plus 7 minus 1. So what I'm doing, guys, is I'm thinking of this right here as the g of t in formula 8. If that's g of t, then if I replace t with t plus 7, I get sine of t plus 7 minus 1. I'm using formula 8, which is up here. This next piece over here, I get e to the minus 3 pi s times the Laplace transform of e to the t plus 3 pi minus the sine of t plus 3 pi. So this second piece, I'm thinking of that as my quote-unquote g of t. Right? So g of t plus 3 pi is e to the t plus 3 pi, and the sine of t plus 3 pi. Right? Now, at this point, you can go to table 7.1 and go, well, I know how to transform sine, right? But I don't know how to transform sine of t plus something, right? So we're going to need to use some trigonometry to massage the expressions inside the curly brackets before we can actually transform them. Yep.
It's probably a stupid question. Where did the sine of t plus 7 come from?
That's the formula 8. So if this is the g of t, right? So the formula equation, it says if when we take the Laplace transform of g of t times the unit step function, it pulls out an exponential, and we end up needing to transform g of t plus a. This I will soon derive.
Right.
It's going to be a calculus 2 thing again. We just have to look at the integral definition of the Laplace transform and sort through the details. It's not hard, but I thought it would actually be more useful for you guys to see this done right here. Okay, so let's see here. So when you come to the problem like this on your next quiz, what you got to do is something like I'm doing right now, which is to use the adding angles formula. So that's cosine of 7 times the sine of t plus the sine of 7 times the cosine of t. That's the adding angles formula for sine. And I still have to subtract 1. All right? And then my next, I've got plus e to the minus 3 pi s times the Laplace transform and laws of exponents, right? So that's e to the 3 pi, e to the t, minus the, well, what happens when you add 3 pi to sine? Well, first of all, what happens when you add 2 pi to sine? Does that change anything? No, sine is 2 pi periodic, right? So one thing I could do is just erase this 3 and make it into a pi. That hasn't changed anything, right? What happens when you add pi to the argument of sine? It pulls out a minus, right? So that's actually just plus sine t using trigonometry. In the function analytic sense of the term. Okay, so now we have done the math enough to know that this and this and this and this, these are all on our table. So we can do it. Here it is. 1 over s plus e to the minus 7s, and then parentheses, I got myself a cosine of 7 divided by s squared plus 1 plus the sine of 7 times s divided by s squared plus 1. That's the cosine term, because the Laplace transform of cosine is s over s squared plus 1. The Laplace transform of minus 1 is just minus 1 over s. And then here, e to the minus 3 pi s. The Laplace transform of e to the 3 pi e to the t is e to the 3 pi over s minus 1, and then plus 1 over s squared plus 1. And there you go. That's the Laplace transform of this three-case discontinuous function. Notice that we were able to treat all three cases with one unified formula, right? And if you understand this example, you realize you can easily do 2 cases or 16 cases just the same, right? The method should be pretty clear here. We just use the gate functions and go from there. So at this point, I probably should derive the Laplace transform of the unit step function and go from there, right? Because we need to justify this equation 8. So let's work on that if there are any questions. Okay. So first, a warm-up. Let's calculate what's the Laplace transform of the unit step function. I'm not leaving myself enough room. Let me start over here. What's the Laplace transform of the unit step function t minus a? By definition, that was the integral from 0 to infinity of e to the minus st u of t minus a. Right? But this integral, we can simplify, right? Think about it. What is this? This is really just the integral from a to infinity, right? Do you see why that's true? What's the definition of the unit step function? It's 0 if t is less than a. So I just dropped the part of the integral which is just identically 0, and I kept the part which is non-trivial, which goes from a to infinity. But we can integrate this thing. And if you don't tell the math professors, I won't tell them. Minus 1 over s e to the minus st evaluated from a to infinity, which is going to give us what? So this piece dies to 0, and we're left with e to the minus as divided by s, which is on your sheet. I put that in, I hand wrote that right under equation 8. You see that? The Laplace transform of the unit step function, 1 over s times e to the minus as. Once upon a time, I accidentally gave a differential equations test where this was not given. And it was fine for some of the students. Some of the students had studied and knew it. But there was about 30% who just didn't, they just did, whenever it had come up, they'd listen to me say it and took it on faith. And then it was bad. So now it's on the sheet. So if none of you heard what I said, it's still on the sheet, so we're safe. Great. Now let's work on deriving equation 8. So what I'm going to do is look at actually I'm going to look at something a little bit different. I'm going to look at the Laplace transform of f of t minus a times u of t minus a, because if memory serves me correctly, it's easier to derive it this way. All right. We'll be able to take this result and get equation 8 from it in the special with just a proper interpretation, okay? So let's work on this one. So integral from 0 to infinity, e to the minus st, and then we got our f of t minus a, u of t minus a. So we can do the same thing we just did which is what? To change the lower bound from 0 to a, that drops, then that means for that range of t, the unit step function's 1, right? So we just have like that, right? So at this point, what I want to do is I want to make a substitution so that this looks like a Laplace transform of something, right? So that means I need to change the lower bound to 0 somehow. And I'd also like to look at the function, I don't know, well, so I definitely need to change the lower bound to 0. What would change this a into a 0? What substitution would do that? What if I let u equal to, oh, how about u equal to t minus a? Maybe that'll work. If you take u equal to t minus a, then t equals to a implies u equals to 0. Hey, that looks like a winner. Du is equal to dt. That's not too bad, right? And all right, so we're off to the races. What's t equal to? U plus a, right? So let's make that substitution. How about infinity? Is infinity still infinity? If you take infinity minus a, is it still infinity? You're like, no, infinity is not a number, so the thing you just said is an anathema. You should think about infinity in terms of an eliminating process, you idiot. Haven't you taught calculus 2 before? Don't you know these things? Yeah, I didn't hear any of you say those things. Let's see here. All right. You're like, we're past the technical jibber-jabber of calculus 2. We don't have to care about that anymore. Am I right? Don't agree to that. You're not supposed to agree to that. Don't worry. Camera at most has the back of your head. You're safe. So that's t is u plus a, and we said u was, so that's f of u, and the dt is du. That's almost a Laplace transform, right? Almost a Laplace transform. If we notice, though, that e to the minus s times u plus a is actually equal to e to the minus as times e to the minus su, and also that this term right here has no u dependence. It's a constant with respect to the integral. We can pull it out. So we'll do that. We have e to the minus as times the integral from 0 to infinity of e to the minus su f of u du, but that is precisely the Laplace transform of f of t, just written in terms of a u integration rather than a t integration. This is nothing more than e to the minus as times the Laplace transform of f of t of s, right? Now that's not equation 8, right? But it's it's the analog of equation 8. That's actually equation 5 in theorem 8. That's equation 5 in theorem 8 that we just derived. All right, so let f of t minus a equal to g of t, then what's that say about what would f of t be then? Well, f of t would be f of t plus a minus a, right? Which then fits the pattern to see that that's nothing more than g of t plus a. And so equation 5 implies equation 8. Right? Therefore, Laplace transform of g of t u of t minus a of s is equal to e to the minus as Laplace transform of g of t plus a. So a couple different formulas running around here, right? And you got to kind of be sensitive to the question you're asking as to which one's the right one to use. I think clearly equation 8 is very useful for taking the Laplace transforms of things like we put in the brown box here earlier, right? What if you're asking the inverse question, though? What if you're asking about inverse Laplace transforms, right? What about that? How would we take the inverse Laplace transform of, I think equation 5 is nice for the inverse Laplace transform. See, because equation 5, what's equation 5 say? It says that the Laplace transform of f of t minus a times u of t minus a of s is equal to e to the minus as times the Laplace transform of f of t. Right? That's what we just derived over there. So look at that. Let's write it in a slightly different notation. This is really big F, right? So if you look at this, what this implies is that the inverse Laplace transform of e to the minus as times big F of s, what's it equal to? It's equal to, at time t, f of t minus a times u of t minus a. This, mechanically, is what we're going to need to solve differential equations with discontinuous terms. This is where the rubber hits the road on the inverse transform. Right there, that's the formula. So that boxed formula and equation 8 are the main tools going forward and backwards with the inverse transform and the forward transform of discontinuous functions. That, in conjunction with the gate technology, allows us to solve pretty much anything of this variety that we want. I should probably, any questions about the, I hope no questions about, yeah, there are no questions. You had your chance. I'll save time for questions about more interesting things later. How about that? Okay, so let's solve a problem. Example. Suppose you're going to solve y prime prime plus y equal to the unit step function of t minus pi over 2. And we need some initial conditions, perhaps. Let's, to keep things relatively simple, getting started here, let's suppose that y of 0 is equal to 1 and y prime of 0 is equal to 0. All right? Let's solve the problem using the method of Laplace transforms. So first step, we take the Laplace transform of the differential equation. This gives us s squared, big Y, minus s. All right? I'm using table 7.2, maybe the third row or something. Notice that you see minus s f of 0, right? S multiplies the initial condition for y. And y prime of 0, like minus 0, but that's not there, right? And then plus the big Y equals to this one, transforms to e to the minus pi s over 2 divided by s. Right? We just derived Laplace transform of the unit step function. I think I just erased it, though. Oh well, I used it though. Okay, so then we solve for big Y. We've got s squared plus 1 times big Y equals to s plus 1 over s times e to the minus pi s over 2. And then, so to solve for big Y, we divide by s squared plus 1, and it's going to give us s over s squared plus 1 plus 1 over s times s squared plus 1, e to the minus pi s over 2. The first term is simple to take the inverse transform of. That's just cosine, right? S over s squared plus 1 inverse transforms to cosine. That's like table 7.1, somewhere in there. The second piece, we're going to need to use, oh man, I erased, well, this is the one I need. I'm just annoyed I erased the other one. I need to give this thing a name. I'm going to call it Pac-Man. There we go. We need to use Pac-Man. So essentially I'm saying, think of this as being the f of s, right? Now, f of s, though, is 1 over s times s squared plus 1. We should do partial fractions on that so we can actually take the inverse transform. Partial fractions here looks like a over s plus bs plus c over s squared plus 1, right? Let's see here. Let's do the algebra. We've got 1 is equal to a times s squared plus 1 plus s times bs plus c. We can plug in s equals to 0. That gives us a nice equation. 1 equals to a. All right. Plug in s equals to, well, we plug in s equals to I. That's nice. 1 is equal to a times 0 plus I times bi plus c. Let's see here. That's 0, of course. We get 1 is equal to minus b plus ic. Oh, it does help us. This is a complex equation, which means it is 2 for the price of 1. So there's always a BOGO sale going on with, complex algebra. And so we can equate the real and imaginary parts, and so doing get 2 equations at once. In particular, we get 1 is equal to minus b, and we get that c is equal to 0. And we didn't even need to look at the conjugate root to do anything, right? Huh. That worked out nicer than it usually does. I'm happy about this. So f of s is equal to, a was 1, so we got 1 over s. We worked, b is minus 1, so minus s over s squared plus 1. So this is a nice partial fractions decomposition for f of s, right? We need to find that, because otherwise we can't calculate the inverse transform of f, right? And in order to put Pac-Man into action, one of the ingredients is you need to know how to get from the big F to the little f, which is to say you need to know how to take the inverse transform of your big F. I can't do that until I have a nice formula for it, but now we do. What's the inverse transform of big F? It's little f. So f of t is inverse transform of 1 over big F, and that is the inverse transform of 1 over s minus s over s squared plus 1 of t, which, by the way, is 1 minus cosine of t. That's f of t. All right? Now I need to use the Pac-Man equation to account for the presence of the exponential in the frequency domain. Right? So let's do it. Y is the inverse Laplace transform of big Y, right? Which is going to be the inverse Laplace transform of the S over S squared plus 1 at time t, I suppose. Probably should put in my time dependence because that is kind of an issue here. Plus the inverse Laplace transform of f of s times e to the minus pi s over 2, where f has been defined on the board there. So then I apply table 7.2 for the first term, and that just gives me a cosine, just a plain old cosine t. And then the next one, I'll write down symbolically to start with. We're going to have f of t minus pi over 2 times u of t minus pi over 2 by Pac-Man. But what is little f? We derived it's cosine of t minus 1. Cosine of t minus 1. So I have to evaluate f at t minus pi over 2. It's function composition. So plus big parentheses cosine, 1. Evaluate 1 at t equals t minus pi over 2. I mean, it's 1, so that's fine. Minus the cosine of t minus pi over 2 times the unit step function of t minus pi over 2. Now you could further simplify that and rewrite the formula in terms of some sort of case-wise fashion if you wanted to, but in my book that's a perfectly good answer right there. Because there's a lot of information that's just manifest in this formula, right? Like what I see from this formula as I look at it, I see a couple things. I see that for time less than pi over 2, the latter term is 0, right? And the initial term, cosine t, is all that's there. Why is there a cosine t in the solution? What's that a response to? I mean, this is a spring mass system with no friction. It's just simple harmonic motion with mass 1, spring constant 1, if you want to think about it. And so the initial cosine t term is just from having the spring, compressed or stretched, I forget what would the case be here, to 1, right? It's initially at rest. It's got a compression, I think, of 1, and then you let the spring go and it vibrates, right? No, I think it's stretched out because after you let it go, its motion goes down. Yeah, so it's got to be stretched out. It's stretched 1 past the equilibrium position. You let it go, and then it oscillates cosine, right? That's the initial condition. But then what happens? At time equals to t equals to pi over 2, this force of 1 turns on and starts pushing on the spring, right? And then the spring keeps oscillating, right? It's still got the spring force acting on the mass. And then after that time pi over 2, this is how it oscillates according to, this term right here. So you can see the response of the system to the discontinuous force when it turns on right there. And you can also check that the motion's continuous. If you look at time just a little bit before pi over 2, what's cosine of just a little bit before pi over 2? What's cosine of pi over 2? It's 0, right? Don't worry me. Yes, cosine of pi over 2 is 0. What is this expression a little bit past pi over 2? A little bit past pi over 2, this is 1. This is still 0. And this is 1 minus, what is this when we plug in pi over 2? Cosine of 0. What is cosine of 0? 1. So this is 1 minus 1. So you see the solution is still close to 0 right after the discontinuous force turns on. So discontinuous force on the system does not necessarily mean discontinuous motion, right? In fact, the motion should be continuous even when the force is not, right? So that will be a feature of solutions, is that they'll be continuous. So the Laplace method of Laplace transforms will find us the continuous solution to the problem. I don't know why you'd look for discontinuous solutions, but let's not do that. Any questions? I know I've showed you a lot of new toys today, but I hope the method is clear if the calculations are worrisome. The method is simply this. We take the Laplace transform of the differential equation, and then we do algebra solve for big Y, and then take the inverse transform to get back. The new thing here is that when you have discontinuous functions, you end up generating these e to the minus as terms, right? We just have to take care of them carefully and mind the fact that they have to be understood in terms of the Pac-Man equation. You have to treat them separately. I don't try to do this and that in the same thought. This I did separate from that. You do the things together with the exponential at once. Also important, I did not bring the exponential into the partial fractions decomposition, right? If you find yourself saying things like a or b or c is an exponential in s, you are doing something wrong. A and b and c are constants. Those are just our way of finding the partial fractions decomposition. So the ABC is just for the coefficient function of the exponential. And on that, we do the same kind of algebra that we were doing last time. This just rides along and must be analyzed through the Pac-Man equation, or if you like, theorem 8. It's Math 200. I found out. That was a very clear no. All right. Now, let us move along. Yeah, it's Brano. So next up, I will talk to you guys about the Dirac Delta function. And I should put quotes on function because technically speaking, folks, it's not a function. And so the basic idea here is to come up with something that sort of models, well, you could think about, we talk about point charges, right? What's a point charge or a point mass in physics? It's somehow you have a finite amount of something at a mathematical point. How do you do that? Because a mathematical point has no extent, right? So what does it mean to have a finite charge? So you suppose you have, an electron, 1.602 times 10 to the minus 19th coulombs, right? That's at where the electron is. Now, ideally, we think about that as a point. What's the charge density? It's 0 everywhere the electron's not, and then it's infinite at that point somehow. It's infinite in a way such that if you integrate the density over that point, you get 1.602 times 10 to the minus 19th coulombs, right? Is that right? Can't remember. Charge of electron anyway, E. So the definition of what I'm talking about, the mathematics of that is the delta function. And so here's the definition. Integral from minus infinity to infinity of, let's say, f of t, u of t minus t0, let's say, is equal to f of t naught. So, oh, and that's not right. That's just the unit step function. That's just not even true. I want a delta there. This is Dirac's delta function. So, in here, more, a heuristic for it is this. This is equal to 0 for t not equal to t naught, and it's equal to infinity for t equals to t naught. But it's infinity in such a way that when you integrate it times a function, it just evaluates the function at that point like that. So, for example, if you were just to integrate the delta function itself, right, what would that work out to? The function that we're thinking about there is just the identity function, the constant function 1. So that works out to just 1, right? So the picture of the delta function, something like, here's t naught. The graph is really kind of boring. It's like 0, right? 0 over here. And this is not quite right, but I mean, there's no, I don't know, how do you draw this? It's an infinite spike. Somehow, the area under that spike is 1. That's what defines the delta function. What's that? Like a tower? Yeah. An MNO. Yeah. No. So now, if you look over here, right, or maybe we look over here. If you think about the unit step function, right, its graph was what? 0, 0, 0, 0, 0, 0, 0, 0. Jump up to 1, 1 like that, yeah? So if you look at these two things and think about it for a little bit, what's the derivative of the unit step function? It's almost always 0, right? Because the unit step function is constant everywhere, except where it jumps, right? Now again, this is heresy in terms of calculus of functions, because one of the things we say about a differentiable function is that it's continuous, right? So what right do I have to talk about the derivative of a discontinuous function? Right? There's some abusive mathematics going on here. But in some sense, the derivative with respect to time of the unit step function of t minus t naught is exactly equal to the Dirac delta function of t minus t naught. So this is the relation between the unit step function and the delta function. Now here's what I like to tell students at this point, is these are both sort of mathematical idealizations. And to define them carefully, you actually use sequences of functions which in some sense limit to these objects. For example, the delta function is actually understood by a series of functions, of so-called tent functions. And so the tent functions might look something like this. And then maybe the next one is a little bit steeper, right? And maybe the next one is steeper still. And yet somehow these are all manufactured such that the area under this sequence of functions I'm drawing, the area is always 1. And then you take, in some sense, take the limit. Well, actually, you don't even do that. You deal with these sequences of functions that all have area 1 under them. Those would give some kind of careful definition for the Dirac delta function. It's not actually a function. It's a family of functions that shares a certain trait. All right? In such a way that we don't really care too much about the details of exactly how that area 1 is being concentrated close to the point t naught. In the same way, if you actually look at a switch, a light switch of a real thing, I mean, we at the start of class we thought about that light switch turning on and off as being an immediate thing, right? But if you actually could slow time down, right, like Ant-Man or whatever, and experience the milliseconds of the light turning off and turning back on, you probably would see something like there's actually a process. Yeah, it's 0, but then maybe this time and maybe that time, it's actually transitioning, right? There's actually a period of less darkness and more light, and it's the various bulbs are charging up and heating up. The things are starting to fluoresce or whatever. There's some time period. But so we don't actually know those details, right? You could have a physical experiment where you don't actually know the details of how you're transitioning between 0 and 1. You just know that you're going from 0 to 1 at a time close to t naught. And the unit step function is a mathematical way of saying, I know that it goes from 0 to 1. I don't really care about the details of how that happens.